My name is Grant. This is my project on radio frequency-based drone detection and state estimation. So just a background, um, we've seen drones gain accessibility throughout, whether it be warfare means or even just private citizen means, and these are creating possible threats to the safety, privacy, and security of not only civilians, but then also there's the wartime effect that we've seen. They've drastically been affecting how wars are fought with their cheap accessibility. And it's often where these audio visual cues of the drones to identify or possibly like see them and what they're doing are too late, whether it be in a warfare scenario or I guess even in the civilian context of a drone hovering and just possibly gathering video feeds. It's hard to see or even hear that drone. So we need to find some way to make an accessible and cheap approach to identify possible bad guys and what these drones are doing so we can possibly help keep the public safe and ensure privacy and security. So one thing we looked at was a kind of lightweight pipeline that's pretty low in computational effort because the main problem with a whole neural network trained on all this data is the IQ data is very dense at 100 to 200 million samples per second. You get gigabytes of data in just a few seconds. So to have scenario-based drone classification, all this just based off of neural network mapping is very data intensive, a lot more data intensive than most approaches for machine learning. So we still took a machine learning approach, but in this case we used autocorrelation, basically looking at possible periodic instances of the channel state information embedded within these drones, and it proved successful in fingerprinting and even some other endeavors, but we'll get into that. And then reducing that dimensionality and then possibly trying to fit a linear model or a nonlinear model across that lower dimensional representation space. And this can provide possible classification of state, speeds, localization, and fingerprinting, and even detection. So what we set out, we made a data set with a drone that was transmitting on 915 megahertz. We had 4 GPS discipline receivers set up across basically a football field size area, and these would gather data with either complete drone power off, so no transmission on 915, the drone transmitting but not flying, and then the drone flying around those 4 receivers while transmitting. And then we also gathered some additional data with the possibility of passive radar localization or identification of these drones just using the 2.4 gigahertz band of Wi-Fi. So the drone doesn't transmit on 2.4 gigahertz at all, and rather we are just looking for reflections of the drone, kind of like a radar, as these Wi-Fi waves bounce off the drone, and we're trying to pick those up and see if there is some distinction that we can identify there. And so when we were looking into this, we identified a data set that already existed with a lot of drone, 8 different drones, and then they ran through 26 different cases of different flights of speeds, altitudes, hovering, ascending, descending, etc. And these were only 1.4 second recordings, but this team published the research with a confusion matrix stating they had almost like a perfect prediction rate of all these 26 cases, which I thought was very interesting, and figured out that their way of actually training their computer vision based model, which would look at spectrogram images, had this temporal leakage, as they would just train on like 80% of the window and then try and test and identify, based off all the other windows, can this other 20% line up with which one? And that's very easy, as there's these small artifacts that could just exist and show up for each timing of recording, as everything was recorded at different times throughout a day or etc. So when we actually do a kind of drone cross-validation, I hold out 6 drones of the 8 and then test these 26 cases and their prediction capability on those other 2 drones I've never been trained on. That prediction rate falls very low with both the computer vision spectrogram approach, which is common amongst most modern research, and our lightweight pipeline of the autocorrelation and dimensionality reduction. However, we did see a benefit with fingerprinting, especially with this very lightweight model. We saw when we looked at basically these 8 drones and looked at trained on all 8, but for 1 through 18 of these 26 scenarios, and then tested on 19 through 26 to then see, okay, can we identify distinct little channel state information across these drones? And that was very successful. A 72% overall prediction rate, and that actually ended up increasing when we used a nonlinear random forest approach to 81%. Then the other graph that you see at the bottom there is not necessarily fingerprinting related, but more a actual localization approach where we utilize basically just time difference of arrival and this packet localization method of the autocorrelation, which we could kind of see up in the upper right of the results section. So in this case, you have the blue line is a no flight, the green and orange are the drone transmitting, or sorry, the blue line is no transmission, the green and orange are transmission. And we see these periodic spikes about every 8 seconds. These periodic spikes represent the packets of the drone actually transmitting. And when we break that down, it actually lines up with the telemetry cadence of about 8.7 hertz. And you can see that with the bar chart on the right. We start to detect definite periodicity, like strength, across those scenarios of the drone actually transmitting. So what we did is we looked at kind of those packets and tried to line up their time difference of arrival across the 3 receivers. And unfortunately, this one, our 4th receiver, wasn't able to record. But we can see overall a pretty decent estimation. If you look at the coloring, so we see darker purple more towards the end of the flight, which is kind of in line with the north or y-axis of this graph, and we see the x-axis items also kind of align, right? As you get down to the lower right, we have that kind of indigo color lining up with the GPS truth, and the yellow color kind of lining up with the GPS truth too. So there is some distinction, although it's rough. Possibly more receivers and obviously a lower signal noise ratio, maybe even more spread out, can help show this time difference arrival a little better. Anyways, and then getting to the right again, we have our dimensionality reduction plots of both PCA and TSNE of the drone not flying, the drone not transmitting, the drone flying. There is some rough separability. You see pretty strong separability in the TSNE plot, and that's where we actually saw significant results with our predictability of drone flying or not from its transmission. We had about a 70% success at predicting if the drone is transmitting or not. And then with the Wi-Fi reflection plots, you can see there isn't much separability, yet we were still getting about a 63% prediction rate for determining if a drone is flying or not under these Wi-Fi reflections. So the main things for future work, looking at more data collection, active millimeter wave radar possibly to see if we can detect drones very far out, and then even more receivers for better time difference of arrival or frequency difference of arrival, and then also a very lightweight mobile phone integration with cheap software-defined radios and stuff to all integrate this into a mobile phone package. Otherwise, thank you very much to Rachel and the RISC colleagues, along with Colonel Matthew Booth and Dr. Anderson, for helping out from the Air Force Academy side. And otherwise, thank you very much. And just to reference, this does not express any of the views of the United States Air Force or the Department of War. These are the views expressed by myself.